You can blame it on me. Jochen, hast du jetzt einen Job? Yes. Eine Computer Science. Excuse me? You are a faculty officer. Witnessing if you're kind of close.
Hello, guys at home. We're gonna start in 7 minutes, so hang in there, and we're very excited for our third event. I don't know. So,
Name tag located.
nice.
Name tag located.
Wenn das der einzige Grund ist, um mich zu probieren, dann vielleicht gar nicht so toll. You meant as a stick, right? Or what do you invented for?
That's it's not like a standard ruler. How to measure it?
Yeah, to I don't know. How to measure
You should get the ruler. Yeah.
I think it's starting at 7. It's starting at 7.
Yeah.
Okay. So you don't need to explain the details. You don't need to explain exactly
Oh, you can
last time anyway, that was
Oh, fun. Awesome. There you go. So we're giving away these. They cannot hear me. We're giving away these Astronomy on Tap pens. If you want to get one, well, you have to join us here at Fiddlers. We will start in 2 minutes.
Ich habe schon gesagt, jetzt weiß ich, wo meine herkommen. Ja, ja, genau. Ich habe dir letztes Mal auch welche mitgebracht.
Extra Vortrag in
Are you changing my script?
Florian Verkauf.
This is mine. So some more things we're giving away. Yeah. Are these? Did you take one of these?
Shooting
Yeah, those are stickers that ISO sent us. So ISO kindly sent us some stickers
What are the
to give
gifts
away.
for today?
Oh, the gifts we will announce it in due time.
I
Yes.
hope today I will win some.
Yes. Yes. I hope so too. Good luck.
You could help me.
Okay. Shh.
Candidate secure their test universal.
Are we ready?
Yeah.
So you go. Hello. Hello. Welcome. We're ready to start. Can we have a round of applause for the team and all the people here tonight? Thank you very much for coming. Take your time to find a seat. I'm sure there is enough space for everyone, and everyone is welcome. So come also to the front, right here on the front table, and we will accommodate you. Okay. So, welcome to another event of Astronomy on Tap Bonn. I am Eleni Vardoulaki, the founder of Astronomy on Tap Bonn and a postdoctoral researcher at the Argelander Institute for Astronomy. And before we start, I would like to introduce the team.
Guten Abend und herzlich willkommen bei Astronomy on Tap. Ich bin Arti Nagarajan, Postdoc am Argelander Institute for Astronomy und Teil des Organisationsteams von Astronomy on Tap Bonn. Bevor wir anfangen, eine kurze Vorstellung des Teams.
Okay. So the team consists of professional astronomers at the Argelander Institute. Here you can see some of them are Toma Badescu, Anna Mikler, Enrico Garaldi, Angus Wright, Arti Nagarajan, Ziad Modak, Sandra Onruch, and myself. Did I forget any? Huh? Sorry, and Laila Link. And today with us is Arti, Anna, Laila, who will also give us a talk, Toma, Ziad, and of course myself.
Unser Team besteht aus professionellen Astronomen, die auch am Argelander Institute for Astronomy arbeiten. Sie sind Toma Badescu, Laila Linke, Anna Mikler, Ziad Modak, Arti Nagarajan, Sandra Unruhe, Angus Wright und Eleni Vardoulaki. Heute Abend sind Eleni, Anna, Sandra, Laila, Toma, Ziad und ich hier.
Cool. So, Astronomy on Tap started back in New York City by professional astronomers who wanted to bring their science to the public in a relaxed surrounding, in a very easygoing way. So what a better place than a pub. So cheers to all.
Astronomy on Tap wurde in New York von professionellen Astronomen gegründet, die ihre Wissenschaft in entspannter Atmosphäre der Öffentlichkeit präsentieren wollten und sie zur Unterhaltung beim Abendessen zu nutzen. Dafür gibt es wohl keinen besseren Platz als ein Pub.
Cool. Astronomy on Tap Bonn will be held every Tuesday, last Tuesday of every month, here at the Fiddler's Pub, with the exception of December, which is on the third Tuesday to avoid Christmas.
Astronomy on Tap Bonn wird immer am letzten Dienstag eines Monats hier im wunderbaren Fiddler's Pub stattfinden, außer im Dezember, da ist es in diesem Jahr der dritte Dienstag um Weihnachten zu vermeiden.
Okay. So, yes. So, if you have questions about our events or related to the talks, if you want to sponsor Astronomy on Tap Bonn or give a talk yourself, so feel free to contact us. You can find us on Facebook, YouTube as Astronomy on Tap Bonn, Twitter and Instagram at AOT Bonn, and our email aotbonn@gmail.com.
Wenn ihr irgendwelche Fragen zu Astronomie
Excuse me.
Okay,
No,
wenn
I'm sorry.
ihr irgendwelche Fragen zu Astronomie oder unserem Event habt, ihr uns sponsern wollt oder selbst einen Vortrag halten möchtet, kommt einfach auf uns zu. Und im Publikum sind auch einige Astronomen. Löschen Sie mit Fragen zur Astronomie. Ihr könnt uns Fragen auch per E-Mail und Social Media kontaktieren.
Okay, I know what happened. You're surprised there are astronomers here. Yes, there are many astronomers around us, so feel free to ask them questions, bug them. They're here for you, apart from us. And they're happy to answer your questions about the universe and explain why Earth is not flat. Okay. Okay. So just to mention, we're streaming live at this moment, so people are seeing us from home. Hello. And if you don't want to be seen live, please don't approach the stage area until the end of the show.
Wir haben einen Livestream von der Bühne, falls ihr nicht gefilmt werden möchtet, solltet ihr deshalb in der Pause nicht zur Bühne kommen.
And if you have questions, write on our live stream. I will be following the chat, and you will have the chance to answer questions to our speakers. So I'm sure they will answer them live.
Wenn ihr uns per Livestream zuschaut, schreibt eure Fragen in den YouTube-Chat. Wir würden sie in unserer Fragesession beantworten.
So now I will call Anna to the stage to introduce the first speaker. Yes.
Not yet.
There you go.
Good evening, everyone. I'm Anna. I'm going to tell you about the speakers today. So the first speaker who's going to give us a talk in English is Florian Pacon. He got his PhD from the Observatory of Paris. He also studied at the University of Paris 11. And after that, after he got his PhD, he actually moved to Bonn. Then he's been here in 2008. He works as a postdoctoral researcher. And one of the big objects that he studies, or the main objects that he studies, is called galaxy clusters. These are one of his favorite objects to look at. And the main reason you look at these things is because they're the most massive objects in the sky. And it's important to look at them in order to understand the structure of the universe. Furthermore, Florian is a specialist on surveying wide areas of the sky, so looking at the sky through X-ray satellites. And that's why today he's going to tell us about mapping the cosmos.
Unser erster Vortrag ist auf Englisch von Dr. Florian Pacon. Dr. Pacon hat an der Universität Paris Orsay studiert und 2008 seinen Doktortitel vom Pariser Observatorium erhalten. Seitdem ist er Postdoktorand an der Universität Bonn. Er ist ein Experte zu Himmelsbeobachtungen mit Röntgensatelliten und forscht vor allem zu Galaxienhaufen und der großskaligen Struktur des Universums. Er spricht heute über die Kartografie des Universums.
So without further ado, let's put our hands together for Florian Pacon.
Okay. Good evening, everyone. Everyone can hear me? Yeah. So it's really great to be here tonight, and I have to say it's actually nice to get the opportunity to convey some of the things we spend so much time and energy on to a wider audience, and not just stay in our small offices doing things. And for that, I want to start with a warm thank to the organization team here and the good job they've been doing for since a few months now. Thank you. And so what I propose to talk about this evening is how astronomers map the cosmos. And you have a few examples here with this 3D maps here on the right, a 3D map of the local stars around the sun, or another one on the left with the distribution of galaxies around our Milky Way. So you can see those maps, and you might have seen many of those already, maybe in newspaper or online science articles. And you may wonder, so what's the big deal? You know, you have a list of sources with their coordinates, you put them on the chart, and you have these maps. So let me introduce a bit more what I'm going to talk about today. And for that, we'll go back to the fundamentals. And the fundamental is this sort of observation of the night sky, which you could get from a very remote, dark area. Of course, for that, you would need your eye to have an instantaneous sensitivity that matches the one you would get from a several minute exposure from a modern CCD camera. So that's a bit cheating, and there's a bit of Photoshop involving also here. But that's really the idea. You have all these nice stars that you can look at forming the Milky Way. And now, of course, professional astronomers, they have lots of other tools to do those measurements. But essentially, what you get is measurement of the brightness of the sources, maybe in different wavebands, and maybe the relative position of those sources, how that evolves with time. Eventually, some polarization of the incoming light. But there's something that you never get directly from the observation, which is the exact position of the source apart from the direction. And this is the topic of the talk. So if you look here on the right chart, you have an example with the famous Great Dipper, well-known figure from the northern sky. And if you wanted to look at the 3D distribution of those sources, here you have a projection in 2 dimensions, where the lines here on the left show the direction of each star, and you have the distance of them. But essentially, the pattern you see on the sky would be the same if some of the stars were closer and fainter, or further away and brighter. And so you cannot really tell of their distance like that. Another example that you have here on this side, with a slightly different view on the right side, with this set of stars that you see from a different angle, where the horizontal level shows the distance to Earth instead of the plane of the sky, and you just have one direction in the plane of the sky here in the vertical axis. And if you want to see how it looks like in the plane of the sky, you have to rotate around the stars, and that's how it would look like that if you rotate slowly. And you end up with, that's a bit slow, you end up with this nice constellation, which is also a well-known constellation from the northern sky. So the topic of the talk is really how people, astronomers, determine the 3rd dimension, the distance to the objects. But before that, we have to go back to how things look like in 2 dimensions, because that's the observation we start from. And because this whole topic of measuring distances actually started very early on in ancient civilization, and that's also the only thing they had back then to start the process. So here you have a map of the stars, and actually things look quite boring in that you have, of course, all these nice stars, and they show some patterns around there, but they're actually quite always the same. So if you subtract like the rotation of the Earth, the 24-hour rotation of the sky, and if you neglect the fact that you see slightly different field of views, different parts of the skies across the different seasons, depending on where you are on Earth, you basically recover the same patterns. And that has been known since ancient times, from the earliest civilization we can trace back. And they all had their own system of drawing figures among the stars and creating constellations from that. So here you see the constellations that we have with modern astronomy, which essentially derive from the Greek constellations, which themselves derive in part from the Mesopotamian, Babylonian constellations, which derive from God knows where, since that's then the dawn of history and you don't really trace the origins back then. What we can say is already the Great Dipper that I showed earlier, the Great Bear, was shown to already be interpreted by some cultures as a bear already in prehistoric times. So that looks kind of boring overall. Fortunately, this is not the only thing happening. So if you look a bit closer, you have a few objects that move. Well, the first thing is you have two obvious objects. You have the moon in the sky, and during the day you have the sun. And those, they follow a path. They don't stay fixed compared to the constellation and the location of the stars. But you also have these other moving bodies. And you can see one here on the right with the yellow curve here across a number of constellations. And that's actually the path of the planet Saturn between 2006 and 2013. If you look a bit closer, what you can see also is this kind of small loops that the path of the planet does about every year. And you have here a zoomer on the same sort of motion for the planet Mercury. And this kind of loop, they're called the retrograde motion of the planets. And they're essentially an artifact from the orbits of the Earth that we are also moving at a different speed than the planet moves around the sun. And then when we cross the direction of a given planet, then for some time, the planet seems to go backward and then starts moving again in the right direction. Okay, so we have those objects. And so these have been known also since very ancient civilizations. And they've been usually termed from the Greeks, again, the seven wanderers, due to their motion on the fixed stars. And that actually word wanderer is the origin, the etymology of the word planet in Greek. So at that time, the Y7 first, it's, of course, you have the sun and the moon, and you have 5 additional planets, which are Mercury, Venus, Mars, Jupiter, and Saturn. And only those, because Neptune or Uranus or Pluto or whichever you want to add, they were not known in the ancient civilization. So very early on, those people knew that the pattern of the star was fixed and these objects were special. And they also realized, obviously, that the sun was carrying heat and light and that the moon was creating the tides somehow. And so it was only natural, and also all the events, the cycles of life, the seasons, the day, had something to do with how the sky moves. And it was only natural to just assume that there was a kind of divine link between what would happen on Earth and those things moving in the sky. And so that's why those planets were often assimilated in many, many cultures with gods somehow. And the names comes from the Latin names of the gods, which come from the Greeks again. And the second thing is that also explains the importance of the number 7 in many of the Western religions. And that's the origin of the week of 7 days, for instance. So you have these small charts here at the bottom that shows in several languages how you say the days of the week compared to the name of the planets. And you see that for the moon, for instance, the Monday in different languages comes from the moon. You see also very obviously in German and English that Saturday and Sunday comes from Saturn and the sun. And you have some indication that Thursday comes from Jupiter, god of the thunder. But you see also, I added the French line because, first of all, because I'm French. The second of all, because that's very obvious in that language that all the names of the days, they come from the corresponding planets that are written on the back. So all these things are essentially the origin of astrology, which is another topic and has been disproven many times by scientific methods. Unfortunately, it still survived to this day. But that explains why it's not like by chance that astrology came up in several civilizations, and that has nothing to do with the power of astrology to predict anything. So before going on, the important thing is that for more than 3,000 years, astronomy was just about explaining the motion of these 7 bodies. And that's why those are the first ones for which astronomers try to determine the distance to us. Okay, so now to explain how you measure that, let's go back to another process, which is, if you think about it, we have the sky projected and we don't know the distance to the stars, but that's also true for anything we see. You don't have like a magic ribbon that stretches from you to one given object from which you can measure exactly the distance, but your brain somehow managed to know how far things are. And that's due to what the binocular or stereoscopic vision. So the idea is the following. So if you look at the upper right plot here, you see that, of course, a given object could have different sizes and distance. But that is solved by the fact that we have 2 eyes. Because a good solution to estimate that is using the most basic figure of all in geometry, which is the triangle. The only way to basically do a polygon with few sides, the fewest sides. And basically, if you have one baseline that fixes the size, the general size of the polygon, the triangle, you just need essentially 2 other quantities, being it angles or other sides, to fully specify what the triangle looks like, and therefore getting the distances. So that's how the eye works. So you have here on the right, this plot showing the 2 eyes of normal vision. You of course have the baseline, which is the distance between your 2 eyes, and is fixed, so your brain uses that as a reference. And if you have like this dark cube in the background, of course with 1 eye you wouldn't know exactly the distance, but then for a given line of sight with 1 eye, the direction that the second eye with which the second eye sees the cube tells you how far it is. So that's essentially the method. You need to define triangles and define the baseline, and measuring the angles, you can recover the distances. So that was applied again for the first time successfully by the Greeks. You must be, yeah, the Greeks. But first, so the first thing, which actually you will see in terms of the timeline, comes last in that case. But the most important thing is to find a baseline. And of course, if you want to see angles of where under which objects would move in the sky, you need a large baseline. And for that, you need the largest you could do being on Earth, which is essentially the size of the Earth and knowing what's the typical geometry of the Earth. So the first fairly accurate measurement that we know of for the size of the Earth is from Eratosthenes, roughly 250 years before Christ. And the concept was the following. So he realized that in this town of Sienne, which is indicated here in the diagram, at the summer solstice. So by the way, this city is the modern Aswan in Egypt. Essentially, the sun was at the zenith, so that if you look into the deep well, you would see that the light rays of the sun would go down to the very bottom. So assuming that the sun was very far away, he just used another position on Earth and looked at the shadow that a vertical object, so one of the first instruments in astronomy called the gnomon, would do in exactly the same date and time. And basically, assuming that the sun is very far away and the direction from which the sunlight comes is always the same, this angle is exactly the same angle that differentiates the two cities in which you do the measurements. And essentially, by measuring the separation of the 2 cities and this angle, you can measure the whole circumference of the Earth, or the radius if you know a bit of geometry, but it was not so clear at that time how to do it. So with his measurement of 7 degrees between the 2 cities of Alexandria in northern Egypt and Aswan, he measured 800 kilometers for the distance between the 2 and came up with a size of the Earth which is really 10% of the one we have today, which was fairly good at that time. Now, one important thing to mention is I I talked about some of the assumptions that the sun is very far away, the light rays always come from the same direction, the earth is round. Actually, if you change your assumptions, you come up with a very different answer. So you have the same sort of observations were known very early on, way before Eratosthenes. And actually, this guy, Anaxagoras, also a pre-Socratic philosopher, was a supporter of the flat Earth model. And using that and the same sort of observation, he inferred that the sun was essentially a fiery rock that was located only like 55 or no, several thousand kilometers from Earth, and had the size roughly of the Greek Peloponnese, which is about 150 kilometers across. And since then, people have kind of reconstructed how we could do that, with essentially his center of life being around Sparta. And what the Greeks considered to be the center of their world was the Delphi, where the oracle was. And comparing the angle and size of the shadow in those two regions, at that time, you could, with the same sort of geometrical reasoning, infer that in a flat Earth, without the curvature, the sun would have to be roughly 6,000 kilometers away and less than 100 kilometers across. The good thing is actually this measurement would change if you change the two baseline that you have here. So actually making those sort of measurements at many points around the globe and finding that the Earth has different distance and size, depending on where you observe, is actually some sort of proof you could use to say that the Earth is not flat. So that's also a good point for the evening. Okay, but this was just about measuring the baseline. So what you're interested in is more like measuring distant objects. And one of the first significant measurements also made by the Greeks was made by Aristarchus. So you notice that it's a bit later than Eratosthenes, but it's still it's a bit earlier than Eratosthenes. So actually the baseline was not known at that point. And he essentially mixed up two different observations. One was that if you look at the cycle of the moon, you have a period of the time where essentially the moon is half in shadow, half in light. And that means that the moon, if you look at the left diagram here, is directly exposed by the sun, and that the direction between the sun, the moon, and the earth forms a right angle, 90 degrees. So with that assumption, he measured the angle between the sun and the moon exactly at the time where the half moon occurred, and he came up with this measurement of 87 degrees. Now, if you remember triangulation, essentially, if you had a baseline like the Earth-Moon distance, or the moon to sun, or Earth to sun distance, you would specify everything. So basically what that gives you is a relation between the distance of the moon to the Earth and the sun to the Earth. So you can relate the two. Another observation that he did in the same time was looking at a moon eclipse. So where the moon passes in the shadow of the Earth, so you see on the upper right diagram, and as the moon moves across on its orbit, it will just go through the shadow cone of the Earth. And by assuming again that the moon essentially moves straight there, you can relate the size of this baseline here where the moon is to the size of the moon just by counting, essentially drawing the moon and counting how many times the moon goes across itself in the shadow cone. And what that gives you is essentially this diagram here that comes from a book from Aristarchus, of course copied later on, and where you have these three triangles that are essentially the same ones, where you have the sun here in the left side, in the middle the Earth, and in the right the moon passing in the shadow. You have these three triangles, and you have relations between all the sides of these triangles because they're just similar and proportional to each other. And so you get another essentially link between the distance of the Earth to the moon, the Earth to the sun, through the size of the Earth. And if you bring all those observations together, you can essentially solve for the only possibility, which is having a fixed sun and moon distance, sun and moon size, relative to the size of the Earth. And that's what he did. Unfortunately, this measurement here of the angle between the sun and the moon at half moon is extremely difficult to make. And one of the reasons it's the timing is a bit different. The angle is almost a right angle also on the other side between the two. And so he estimated 87 degrees, but the current measurement is more like 97.8, 99.89.8, sorry. And because that's a tiny, it is extremely close to a right angle, that makes a huge difference in the distance. So that means his scale to this distance of the sun was wrong by a factor 20 times closer than we know it is today. Same for the size of the sun. And unfortunately, this remained the reference for Ptolemy and all the later astronomers, and remained the reference until almost the 17th century. So now is the time where I need to make a small leap in time, because otherwise I will take the whole evening just for myself. That could be nice, but I think Leila wants to say something also. And so I will just jump over the different methods that we use to get rid of this factor 20 and make more accurate measurements, essentially based on planetary transits and an accurate theory of gravitation. Just to mention that now we cheat a little bit and we don't do any of these for the solar system. And what we do is essentially we have nice radars and we can just send a powerful wave to a planet and measure the wave that comes back and just get to the distance like that. And we also have this nice laser that we use to measure the distance of the moon, thanks to the reflector that the Apollo missions put on the moon. Again, another proof that the Apollo missions did exist. So I'll skip all of this and go to the next step, which is if you want to look even further, what is the distance to stars? And for the distance to stars, you have this problem that they are so far away that the tiny angles that you would see with the Earth's baseline doesn't help. You cannot measure it. So what you need is essentially a larger baseline. And the solution was found essentially around the same sort of times, 17th century, which is to essentially take advantage of the rotation of the Earth around the sun. And as the sun is at the two extremes of its orbit around the sun, you could look at the position of the stars at those dates. And that gives you an estimate of the triangulation with 2 times the distance between the Earth and the sun as a baseline. And that's called the stellar parallax. So you have an example here where you have stars in the background that are distant enough that they essentially don't move, and a much closer star. And you see the 2 different directions here in this diagram. And you have on the left and right how the star in purple appears in the sky in those 2 different dates. So the first stellar parallax was measured by Friedrich Bessel in the 19th century, early 19th century. And that's what we use now to make a map of the stellar structures around us. So the status of the art is this satellite from the European Space Agency. It's nice for once to talk about the European Space Agency and not always NASA, which we hear everywhere. You'll hear about it a bit later, I think, again. And the result is this nice map that is difficult to show with this kind of light, but if you had the computer screen, you would see is amazing. It's showing the position of course, this is projected in the sky, of a billion stars for which the distance was also measured by this Gaia satellite. And this is thanks to a positional accuracy of, I don't even remember how to say that number. It's so small. It's such a small fraction of a degree. Well, 3 zeros, I think. And so you also see in this night sky, you can also see those 2 clouds here, which are the Magellanic Clouds, the 2 dwarf galaxies that are the closest neighbors to the Milky Way. And even there, you can measure position of stars with Gaia. Okay. The drawback is that if you actually consider the distance that you probe with Gaia, this is actually this small circle in red here shown over a kind of artist illustration of the galaxy. And what that means is you're just uncovering a small fraction of the galaxy at that point, and you don't even talk about extragalactic scales. And actually, this nice map that you see with the galactic plane is some sort of an illusion, but what you see is not the galactic bulge in the center, but just denser galaxy star distribution, sorry, in the direction of the center of the galaxy. And if you look from outside at the distribution in 3D around the sun, you actually see a bit of the plane of the galaxy and why it's denser around here, but it's actually just a cloud around us. It's not like the huge galaxy that you're probing. So how do you go further? You have two methods for that. And they are a bit different, but that's something you also use with your eyes. So if you think about it, you use your stereoscopic vision to estimate distances. But if you close an eye, and if you look at something, you still have an estimate of the distance of things. And the main things we're all using is the standard ruler. So that's the idea is you have a ruler, you put it here, it has a given extent, a given angular extent. And if you put it further away, it has a smaller extent. And basically what you're doing like that is triangulation, but knowing that the two angles at the top and bottom of the ruler are the same, and knowing that the ruler is the baseline. So that's a reverse triangulation, if you will. And that's what you have with this small illustration here on the right, where that lady is essentially a standard ruler of, let's say, 1.70 m maybe, and the guy in the background should have roughly 1.70 m, and you know that it's not a giant crushing a guy, it's just people with different distances. Unfortunately, I won't talk about it because it's interesting, but it's more complicated to use in practice for the extragalactic distance scale. What we use more frequently is standard candles. Standard candles are a bit more subtle. The idea is if you have a candle of a fixed brightness, or it could be a light bulb in that case here, which you see through the window, its intrinsic brightness would be diluted over the whole sphere, so that if it's further away, as you know, it appears dimmer. And basically, you have this known relation between the distance and how dimmer the candle gets. So if you know the intrinsic brightness of a source, you can use it to estimate the distance to the source by seeing many of those. So we need to define standard candles. The first one that are really of central importance in defining the extragalactic distance scale are called Cepheids. So Cepheids were discovered in the early 20th century, a bit before even. And this lady here, Henrietta Swan-Leavitt, studied a sample of them and found these nice properties that, well, first let me mention what they are. They are variable stars, so that's why they have something specific. So if you look at them at different days, their brightness would change just because the intrinsic brightness of the star changes. And she studied things like this diagram that you see in the bottom here, which is as a function of time, how the brightness of the star change. And it's essentially a star that is reaching an unstable stage of its life, and it's essentially experiencing radial oscillation, and the brightness of the star changes with the size of the star at the same time. So what she did was essentially, of course, this shows there's a fluctuation in brightness. So that's not in itself something that makes it a standard candle. What makes it a standard candle is that actually she showed with a first small sample that there's a correlation between the luminosity, the intrinsic brightness of those sources, and the period of the oscillation, how frequently the pattern repeats. And so basically, by observing the light curve, how the brightness of the star changes with time, you can infer how luminous it is, and from what's its average luminosity and its observed average flux, you can infer the distance. And that's how you can map the scale to the local galaxies. And you have here an example of the universe very close by to Earth, where you have on the right here, you have the Milky Way. And the other big galaxy here is Andromeda, the kind of twin to the Milky Way. And they all sit in this kind of local group with tiny galaxies. And you have here the Magellanic Clouds very near the Milky Way. And this gets across about 3 million light years. and the distance over which you can use Cepheid is about 20 million light years. So that's great. We can find distance to the nearby galaxies, but that's still not something that you can use to get the large-scale structures of the universe. I mean, this is just a few million light years, and you get barely 10 times more than this. So you need, again, another step. And this other step is to use another standard candle, which are the supernovae, in that case, so-called type 1a supernovae. So supernovae, they're essentially the end stage of stars. And you have different types of supernovae, but essentially it's a stage where stars become unstable and either implode or explode in some way. You have an example here from a supernova observed on the right, a supernova observed in 1994, where you have the nice galaxy here, and you see a small bright spot which showed just for a small period of time, and that was this explosion of a star. When you look at supernova that are further away, what you see is essentially a tiny dot, like you have this on the upper left here, upper right from you, sorry. You have this tiny dot that increases in brightness in time, and if you look at the difference, you see that there was something more luminous inside. So the type 1a supernovae are a specific kind of object because they're essentially very compact stars that already reach the end of their life, but they live with a companion, a very massive companion. And because they're so close, this compact object actually attracts the matter of the companion, disrupts it, and somehow gains mass by just stealing mass from the other star. And this star that is already very compact, actually, by increasing its mass, it will at some point yield a threshold where it becomes unstable and explode. And this threshold is the same for all the stars. That's why we believe those type of supernova are extremely stable and give the same sort of luminosity. Of course, people working the theory of supernova will tell you it's much more complicated than that. But empirical observations show that to first order it works well. So I want to show you this because I don't have to show it, but I like it so much. It's one of the best known type 1a supernova because it's really of historical importance. It was observed by Danish astronomer Tycho Brahe in the 16th century. And actually, several centuries after that, we found it back. And that's known as the Tycho remnant. So there was this explosion a while ago. And the cloud that you see here is all the material from the star that was ejected at the time of the explosion. And what's so great about, so I must say for the first time in this talk, that's an X-ray image. That's the only one that I will show, observed by the Chandra satellite. And the great thing is it happened several centuries ago, and we can still observe it, see it, and something that is rare on this kind of scale, we can even see it move. So we've observed it for several, like a decade, and if you browse through the different images, you can see the outer shell of the supernova remnant still expanding from the explosion. So let's have a look here, if you move. So yeah, I think that's a really cool image. Anyway, but the point is those supernovae at the time of their explosion can be used as a standard candle. And that's the final step on how we reconstruct. You have other ways than supernovae, but that kind of measurement here is the final step of how we measure the extragalactic distance scale. And that is done by, of course, measuring the distance to different supernovae. But as you would imagine, you have just rare supernovae in some galaxies. You don't have supernovae all the time in all galaxies. So you can measure the position of all the galaxies. You have like maybe one every couple of centuries in each galaxy or something like that. So what you do for that is you use some finding from cosmology. That is, we know now the universe is expanding. And this is a small sketch here on the left that shows you how it's happening. So you have time going from top to bottom. Time is elapsing, and you have like the Earth and a given galaxy. And as the universe is expanding, those objects, they do not move, but the space between them, it just is stretched, and that increases the distance between them. And that stretching has an important side effect. It's that the light that comes from that galaxy is also stretched as it goes to us. So when it starts, it has a given wavelength, a very short wavelength, meaning energetic photons and light. And then when you observe the photon as it travels a bit later, it was stretched by expansion. So if the Earth was there, you would observe it at a given wavelength. That is not the base wavelength on which it was observed. And if you put the Earth even further, with more expansion, it's stretched even more, and it has even larger wavelength, which means in the optical it appears redder. So these blue photons become redder, thus the name redshift from the cosmological redshift. And that is mainly observed by looking at emission lines, which are features of very characteristic wavelengths in the spectrum of galaxies, how they are moved in the observed frame when you observe them. And basically, you can measure that redshift for all the galaxies, and that's much cheaper than finding a supernova in a galaxy. So what we do is we build those kind of diagrams here, where this redshift, so on the right side, where the redshift is linked to the distance. So that's actually for people who remember their lectures from high school in maths. That's actually the logarithmic scale. That's the logarithm of the distance here, the distance modulus. So because the distance scale is so wide, so you link the distance with the redshift, and you have all these points here are observed supernovae. And you can reconstruct the link between the redshift and the actual distance of the object. And with some cosmological models, you can even find predictions that actually match these observations. And by using those predictions, applying them to a large sample of galaxies with known redshifts, you can reconstruct the distribution of galaxies in the universe. And that is the sort of thing you obtain here, where you see this interesting large-scale structure with lots of filaments of galaxies and void between them. And so that's the end of the scale I wanted to probe today. I will just finish by showing you this very cool video by the same collaboration, the Sloan Digital Sky Survey, where essentially they took all these galaxies, and instead of putting dot in a diagram, they just put them in real space with the actual observed image put at the real scale, and they made this nice movie where you fly through the galaxies and the large scale structures of the universe. So I suggest we have a look to it, and then we can move on to questions while it goes and anything else in the program. So thank you. Okay. Yeah, if people want an explanation, so I already said you essentially make a 3D map of those galaxies, putting them at different positions. And what you see here is once you have the map and putting the right image of the galaxies, you just change the position of the camera and you fly through the structures of the universe. And you can see all those sort of filamentary structure. Here you have groups and clusters of galaxies, which are actually the objects I study in the X-rays. But yeah, that's again a different story, so I won't talk about them today.
So how far does this observation go? Like
This one from the Sloan, I don't know. That's a good point. So it goes to redshift 0.4, 0.5. We are so used in talking in terms of redshift that we forgot the actual scale that it corresponds to. The other thing is I have numbers in megaparsecs in mind and not in light years, but it's 3 point. No, yeah.
Well, thank you so much for the talk. Very interesting talk.
Thank you.
So we're gonna have questions now. The couple of reminders for the questions and for the German announcement. We give a free beer or soft drink for free to the first question asked of the evening, just to motivate you a little bit for non-astronomers. So all the colleagues, be quiet. And if you ask questions at any time, you can participate in a raffle. So here, Eleni and Sia have tickets, and they will go to your table whenever you ask a question. and you can win a beautiful 2019 calendar. Yes, with pictures of telescopes.
Vielen Dank. Gibt es Fragen, um euch zu motivieren? Gibt es für die erste Frage von einem Nicht-Astronomen ein Bier oder einen Softdrink und Sonne? Außerdem kommt der Name von jedem, der eine Frage stellt, in einen Lostopf und ihr könnt einen Astro-Kalender gewinnen.
Hi. Yeah, my question is, did any of you ever observe or do this experiment with a laser on the moon?
Unfortunately, no.
So, I mean, most people know it from the event.
I mean, no one here in the committee. I don't know if some astronomer in the room did.
Is it really hard to do? You know that?
Is it really?
Is it complicated?
Yeah. You need a fairly powerful laser and read the right direction. So you cannot do that at home usually.
But with your student equipment on university, you can do it.
we I don't know because the thing is we don't actually have much lasers in the astrophysics department. So you would have to ask the physics colleague if they can do it.
But on your opinion, there must be, if we trust the person that he did the experiment, there's no way that the laser bounces back without a human-made error.
I think that could be possible, but
So still room for the conspiracy people.
yeah, I mean, there's always room for the conspiracy people. You know, the concept is they want people to prove that something is true, while science moves the other way. It's like we find a theory that we find explains a lot of things, and we try to kill it. And the theory that survives is the winner, essentially. And while you can never prove that something is true, because you can always add assumptions and put other things on top of that and make a different theory that will also be true. What you can do is prove the ones that are really false. That's much easier to do, much cheaper. And usually the people working with conspiracy theory, they have their own ideas and they say, you're wrong, prove that you're true, while we actually work the other way. So that's what complicates a bit the comparison usually.
I believe the moon landing, so I'm not.
Thank you for the question. Also gibt es Fragen gerne auch auf Deutsch? No questions?
Everything clear? I have a question. Maybe the public is interested about it. For a long time, we assumed that the Earth was the center of the universe. For a long time ago.
Yeah.
Did that affect the measurements towards the distance to the sun or to the moon that make the difference with that assumption?
Oh, that's a tough one. I think in principle, no. The thing is, the main difference is if you put the Earth at the center, the orbits become extremely complicated, explaining the motion of things that move around the sun, but relative to the Earth that also moves around the sun, makes things look complicated. So the distance themselves, they're always the same. It's just you need a very fancy mathematical model with lots of loops, and you need to add a lot of stuff to actually recover with the theory the actual distances. While if you place the sun in the center and have ellipses around them, you just need a few parameters per planet and you specify everything.
Questions?
Ich sage es aber in Deutsch, und zwar ist die Frage, wie hat man in der Antike die gleiche Zeit gemessen in Aswan oder Aswan und in Alexandria? Da muss man ja auch bedenken, dass man zur gleichen Zeit messen muss. Wo ist das schwierig?
We're going to have a translation.
Yeah. So essentially, I think I understand. So the question, if I got it, is how in ancient time you make sure that you make the measurement in Alexandria and Aswan at the same time, exactly. So you have actually something very nice in the sky that does that for you. One is you choose the right day, which is the summer solstice, and everyone knows the dates. And then for the time, of course, as the sun moves around in the sky, the size of the shadow will change. And typically when the sun is at the zenith is when the shadow is the largest. And so you measure when the sun is at the zenith in the two cities. What did I say? Yeah, yeah, exactly. So thank you. Maybe for the people on YouTube who may correct, the shadow is the smallest when the sun is at zenith, of course.
What will be the next generation of satellite after Gaia?
I don't think there's currently a Gaia successor plan for measuring the parallaxes to stars. Actually, yeah, that's a good point. I don't know of any mission that is planned to do that right now. I mean, there's already a lot of new things to do with Gaia, and people will have a lot of work with that. I think that there are many more missions to actually measure supernovae and move on to the largest scale. But yeah, I think there's no mission plan. Well, probably people have plans, but no mission accepted right now.
Any other questions?
Okay, I just have a question about the last plot you showed, the redshift at distance.
Yeah.
If the universe is constantly expanding, what the hell does this distance mean? Is it the distance at the time light was emitted, or is it the distance now, and then the expansion is changing?
Yeah, so I simplified a little bit because it gets extremely tricky when you talk about distance measurement in the context of the expanding universe, because you have to explain that in the context of general relativity, which also means that the universe has a special curvature. So things get extremely difficult. One simple way of saying it is first that the models that we use to recover this kind of measurements, they predict essentially the expansion rate with time. And so we often make use of this reference called the comoving distance, which is actually the distance when you subtract the expansion of the universe. So we relate this comoving distance to a given redshift. But the ones that we typically use here is even more complicated. It's called the luminosity distance, and it explains how the flux of a source decreases with the redshift. And that you have several things to add. The fact, for instance, that if photons get redshifted, then their energy decrease. So that adds another factor which scale also with the redshift. And you have two factors like that, and you end up essentially with a different definition for that distance that you would have for another definition. No.
I think if I can say something, and this is why I explained this a very long time ago, is if you imagine you create a grid, right? And you put two objects, the sun and the earth, and you say, well, they have a distance of 3 squares in my grid. You can stretch that, right? And then you can make it very far away in our perspective. But if you measure it again, you say, well, they're still 3 grids away or 3 squares away. It's just in some way they still fixed in some distance. It's very complicated to allow.
Yeah. So the number of grid squares would be the comoving distance, but if you wanted to measure the actual distance, it would be much larger.
Any other questions?
There's one from our live feed. Can I read it?
Yes, you can read it.
I will not say it came from Astronomy. So there is a question from our live feed, and Eric asks if does the movement of the planets change our fate?
Do they change our fate? Well, first of all, you have to define what fate you're talking about. But I think in some way it does, because we can predict essentially where the planets are moving, and we can predict that the orbit of Earth is extremely stable and will stay stable for a large amount of time. And we also know from stellar evolution that the sun will at some point go one of these giant phase where like the giant companion I showed in the supernova explanation, and that actually that will go past the orbit of the Earth, so that the Earth will be burnt at some point by the sun. And we know that because the orbit of the Earth is so stable and won't change much by then. It will change a bit, but so So in some sense, by knowing the orbit of the Earth, we know that the fate of the Earth is to be burned by the sun.
They changed the date. Any last questions? I have one question. One more.
I just have to ask. I just have to ask. Did the Greeks invent everything?
Um, I think no, but well, first of all, I mentioned how much they actually borrowed from the Babylonians, which is often understated. Um, a little bit from the Egyptians, but they were a bit less into like the more accurate measurement of things and more into like vague concepts. Um, but yeah, of course, they borrowed from everywhere. The point is, as you go back in history, it's more and more difficult to trace the origins of things. And for instance, for the Babylonian, we don't really have the documents to know where they borrowed from. So it's very difficult.
Any other questions? Last minute questions? Answer here. Okay, so let's thank the speaker one more time. Before we go for break, we have a couple of announcements. First of all, please remember to talk to the astronomers. We're always happy to talk to you, explain things, discuss things, conspiracy theories, whatever it is. So a bunch of us around here. The speakers are still here, so after the break, just come and talk to us.
The break is still far, far away, far, far away. So if I manage to set this correctly. Okay. So, hello. No, that's not it. Where is my nice slide? Oh, gone. Okay, it doesn't matter. We're missing the slide about Instagram. Okay. Sandra? So, in the meantime, did you enjoy your first talk? I think I really liked it, the part that Greeks invented everything. I didn't listen to the answer of the question. I didn't care. So I would like the slides that contain ISO. ISO. Thank you very much. Okay. We have a lot of things planned for you today. We have some free Astro stuff here in the table in front of me, and we're giving prizes. One of our sponsors is the European Southern Observatory, ISO. ISO is an intergovernmental science and technology organization in astronomy and has 3 unique world-class observing sites in the Atacama Desert region of Chile. It hosts state-of-the-art telescopes like the Very Large Telescope Array, the VLT, and the Atacama Large Millimeter Submillimeter Array, ALMA, among others. And ISO kindly sent us a lot of stuff to give out to you, so every time we give a few.
Lasst uns weiter im Programm gehen. Wir haben heute wieder für euch kostenlose Astro-Sachen. Dieses Mal gibt es Sticker, Buttons und vieles mehr von European South Observatory ISO. Die ISO ist eine internationale Wissenschafts- und Technology Organisation in der Astronomie mit 3 exzellenten Beobachtungsplätzen in der Atacama-Wüste in Chile. Sie flasht auf top-aktuelle Teleskop unter anderem das Very Large Telescope Array VLT und das Atacama Large Millimeter Submillimeter Array ALMA. Die ISO hat uns netterweise diese Astrosachen für euch zur Verfügung gestellt.
Yes. You will also have the chance to win some gifts with a logo of Euclid, like beer glass, notebook, and a very nice shopping bag. So Euclid is a European Space Agency mission to map the geometry of the dark universe, the universe that we cannot see. Euclid aims at understanding why the universe gets larger with time and what is dark energy we astronomers talk about, but we don't know very well yet.
Ihr könnt auch Geschenke mit dem Logo von Euclid gewinnen, zum Beispiel ein Bierglas, ein Notizbuch und einen Einkaufsbeutel. Euclid ist eine ESA-Mission, das dunkle Universum zu untersuchen. Mit Euclid wollen wir verstehen, wie sich das Universum ausdehnt und was dunkle Energie ist. Etwas, wovon Astronomen viel reden, aber noch nicht gut verstehen.
So feel free to take some stuff here from the table. We have stickers and postcards and some very nice Astronomy on Tap pins that I'm actually wearing one of them. So come on later and take one. Okay.
Gerne etwas in der Pause oder am Ende aus und stellt uns alle eure Fragen.
I have a crisis here. It's like it's not working. So cool. And the next slide. Yes, no. It's it's great. It's great. Yeah. We're on track. It's great. No worries. Excuse us. We're too excited. So for the next events, we would like to give you more stuff astronomy on tap related, like those pins, but print coasters and maybe mugs or whatever we can. So we kindly ask for donations. Today we have 2 pint glasses that Ziad will circulate around, and they have 2 pictures. So the theme of today is Mars and the probes of Mars. So are we faithful to curiosity, or we are totally into insight? So I don't know if you heard it yesterday. Big news. NASA landed a probe on Mars. So I personally watched it live, and it was awesome. And the goal of InSight is to drill into the surface, beneath the surface of Mars, and study what is under the surface. And Curiosity landed back in 2012 and is studying the surface of Mars and still doing a very good job. So pick your favorite, and thank you very much for your donations.
Wenn euch das Event bisher gefallen hat, würden wir euch gerne um eine kleine Spende bitten. Mit dieser Spende könnt ihr euch auch eine wichtige Frage beantworten. Das heutige Thema ist der Mars und darum fragen wir euch, was war die bessere Mission, Curiosity oder Insight? Curiosity ist 2012 auf dem Mars gelandet und untersucht die Oberfläche. Insight ist erst gestern gelandet und soll herausfinden, was unter der Marsoberfläche ist. Wir lassen 2 Biergläser herumgehen. Bitte befüllt das Glas für die interessante Antwort. Vielen Dank.
Also, let me press this button. Yay! Okay, so don't forget to take a photo with our Instagram frame and tag us on Instagram at AOT Bonn. And every month we do a draw, and the best photo wins. So the winner of last month can be seen here. It's me. Are you an astronomer, Sandra?
No.
No, okay. Then you win.
Und vergesst nicht, ein Foto mit unserem Instagram-Rahmen zu machen. Postet eure Foto und auf Instagram tagt uns und vielleicht seid ihr die glückliche Gewinner, die beim nächsten Mal einen astronomischen Preis bekommen.
And now we will give the prize to the winner. So come and claim your prize. And the prize is, can maybe Anna help us with the prize? The pint glass from, the beer glass from Euclid. So, yeah. So it's a, and it has the distance, and it has the distances. So